Hello. In today's session, we would be looking at an important concept in the design of databases, namely what is called as the conceptual design of databases using a model called the entity relationship or the ER model. Now, you might have heard somewhere that databases today are based around the relational model, right, where the fundamental aspect of the building block of a database are tables. So, where does this ER model come into the picture, and what is its relevance? Why do we need something like an ER modeling for databases? So, in order to answer that question, let us begin with looking at a small description of what a typical database design process looks like. This is just a simplified representation of what a database design process looks like. However, this captures the gist of most database design processes. Whenever we talk about databases, we should always remember that databases are always embedded within some kind of an application context, and this is called the information system within which the database is embedded. Okay, so a databases could be embedded within, for example, for a banking solution, the databases could be embedded within a railway reservation solution. They could be embedded within a university setup, a company, whatever. Okay, now whatever this this setup is, this context or the information system context is what is called as a UOD or the universe of discourse. The universe of discourse basically tells us what are the building blocks that make up this context within which this database is going to be run. Okay, now generally when we talk about designing a database system, we first talk about looking into the UOD and collecting requirements from the UOD. We have to make an analysis of the UOD, saying for example, suppose we want to build databases for a bank, we have to first identify, or we have to first understand how does the bank conduct its operations, what kinds of operations do they have, and what are the rules, what are the norms, and what identifies a correct operation from an incorrect operation, and so on. Okay, and that is going to give us two kinds of requirements. The first is what is called as database requirements, or you might also term it as data requirements, and the second is what is called as the functional requirements. Now, as you might have imagined, the database requirements are handled by the DBMS or the database management system. Okay, however, a DBMS by itself is not a complete solution. To give you an analogy, DBMS is something like an engine. Okay, now we can't just have an engine, we have to build a car around it, or we have to build a bus, or whatever it is around it. Okay, so this this layering around the database system is what is called as the application program, or the information system. So the functional requirements go into designing the application program, or the larger information system within which the database is going to be built. Okay, now continuing with this process, we take the database requirements and come out with a first level, or what we call as a high level conceptual design. We have to first understand how this database requirements look like. What are the different data elements and how are they related? We need to first understand in a way, or rather represent it in a way that is understandable by human beings rather than computers. We have to first understand the solution problem first before we give it to the computer, right? So so database requirements go into what is called as the conceptual design, and the output of the conceptual design is what is called as a conceptual schema. Okay, now this conceptual schema is what we are going to be taking up today in more detail. Okay, but going on with the process itself, let us see what happens with the functional requirements. Okay, so functional requirements also go through a similar similar process where you do functional analysis. You analyze what are the different functions. If it is a bank, what are the different functions? Opening an account is a function, or making a bank transfer is a function. Now, what are the constraints that that hold up these functions? What is a correct function? What is an incorrect function, and so on. Okay, so once this functional analysis are made, we get what are called as high level transaction specifications. In fact, we will be revisiting this topic called transactions as a separate module, where we will see that many times we need to club different operations of the database into one logical unit, or what we call as a transaction. Okay, now transactions are what are the building blocks of the functional requirements, or the functional analysis of the information system. Now you can also see down here that all of this until now all of these are DBMS independent process. Okay, so what is meant by DBMS independent process? It means that doesn't matter whether you are using an Oracle database or an IBM DB2 database or a MySQL or Postgres or whatever it is, you will have to look at the UOD, you will have to understand your UOD, you have to come out with a conceptual design which is in no way relevant to the actual implementation which the DBMS does, and you have to do a functional analysis, okay, which is completely independent of the DBMS that we are using. Next comes the DBMS dependent processes. Okay, so we ended up with the conceptual schema previously in the database stream. You can see that there are two different streams of processes happening. One is the database stream, and the other is the functional stream or the application stream. Okay, so in the database stream we had ended up with the conceptual schema. Now the conceptual schema in turn is should be transferred into what is called as a physical design. Okay, now what is physical design? The physical design actually tells you how the data itself resides on the database, on the computer. Okay, so obviously this is a DBMS dependent process. Okay, so the way even though there are many standards that exist now, the way that, let us say, Oracle stores its data would be different from the way DB2 stores its data. Okay, even though they adhere to some standards, there are going to be slight variations. Okay, so this physical design results in what is called as an internal schema, or the schema which actually goes into the DBMS. Okay, and similarly the high level transaction specifications that we had talked about are also going to impact the physical design of the database. I mean, suppose certain kinds of operations have to be performed together, it makes sense to design them near to one another, so to say. Let me just use the word in a slightly loose fashion, near to one another, so that it becomes easier to handle transactions on. Okay, so you get inputs both from the conceptual schema and from the high level transaction specs in order to make your physical design of the database. Similarly, the application stream goes off into application program design and transaction implementation, and finally the application software. Okay, so from all this, now we are going to concern ourselves in this session with just one aspect of this entire process that we looked at, namely the conceptual schema. Okay, now what is a conceptual schema and why is it important for database design? Okay, so let us have some observations about what is a conceptual schema. We just saw that the conceptual schema is an outcome of the high level conceptual design of a database. Okay, so this is one of the first things we are going to do. We are going to understand our UOD or the universe of discourse. It tells us what kinds of data that the UOD is going to handle, and based on this we are going to come out with a high level design. Okay, so it's a very concise description of the data requirements, what kinds of requirements do users need, and how are the data related between one another, and so on. Again, let me take a brief example. Suppose you are building a banking solution. Okay, one of the first things that you are going to note is that in a bank there should be accounts, there should be customers, there should be customers or account holders or whatever you call them. Okay, and there should be, of course, monetary transactions, and there should be some kinds of logs and ledgers and account books and so on. Okay, so all of these represent some kinds of data elements. Okay, and a very high level conceptual design would identify each of these data elements and say this is how they are related. Okay, so it includes a description of what we call as entity types. These are the entities that make up the UOD. Okay, in a bank, the customer is an entity, an account is an entity, a ledger is an entity. And similarly, there in any other UODs there would be several different entities like that. Whether it is a railway reservation system or a university or whatever, there are going to be different kinds of entity types. Okay, and there are relationships across entity types. Okay, so customer holds an account, and an account transfers to another account, and so on and so forth. Okay, so there are relationships between different entity types, and there may also be certain constraints that are imposed either by physics or or by the UOD itself. Okay, in a bank, for example, one might say that in an SB account, balance may not go below 50 rupees or whatever. That's a constraint that is imposed by the UOD that says that you cannot have less than 50 rupees in your account in order to make it in order to make it working. Okay. On the other hand, there could be other constraints that are imposed by physics itself, the physical reality. For example, if you are modeling a railway reservation, you can't obviously have two trains starting at the same time from the same place, from the same platform, so to say. Okay, simply because those two cannot exist. Okay, at the same time. Okay, so there are different kinds of constraints that exist among data elements, and this is what we are going to capture during the conceptual design. And another thing to note here is that a conceptual design has no implementation details. We are note that earlier we had noted that a conceptual design is a DBMS independent process. Okay, so that means we are not really worried here about how this conceptual schema is going to be implemented within a database system. And the main idea of a conceptual schema is ease of understanding. We should be able to say to your end user, this is what we have understood from your description, this is what we have understood of your needs. Okay, and and your end user should be able to understand your understanding, so to say. Okay, so he should be able to understand your understanding, even though the end user may be a non-technical user. Okay, so the main idea behind the conceptual schema is ease of understanding, and it is used mainly for communication with end users who are of a non-technical nature. Okay, so here is a small example. An example company database. Okay, so suppose we look at a company. What are some of the first things that we can identify? Some of the first things we identify are company, of course, has employees. We can see them. Okay, then company has departments. Each employee works in different departments and so on. Then once we start speaking to employees, we find that there are also different projects, and each department has one or more projects, and a project may span different departments and so on. Okay, and once we start to the HR, talk to the HR department, we note that each employee also has some dependents, and they're also covered in some way or supported in some way from the company and so on. Okay, now if you look at this slide carefully here, we see that there are two different kinds of things that we are noting here. All these things before the colon, we see the things like departments, projects, employee, dependents, and so on. And after the colon, you have terms like name, department ID, manager, or name, project ID, location, or name, PAN number, address, and so on. Okay, so what this says is that all these names before the colon, like departments, projects, are entity types. Okay, they are different entities. A department is an entity, a project is an entity, employee is an entity, and so on. But the ones after the colon, like name or manager or location and so on, are what are called as attributes of this entity. Okay, that means they belong to this entity. For example, the name occurring after department here belongs to this department. The department ID belongs to this department. Similarly, the project ID belongs to project, and address belongs to employee, date of birth belongs to employee, and so on. Okay, so it not only belongs to employee, it also tells us, or it describes something about the employee. Okay, so if there's an employee has a name, an employee has a PAN number, if he is paying income taxes regularly, that is, he has an address, he has a salary, he has well, he or she has a gender and date of birth and so on, right? So all of these attributes define what is an entity type and what are the characteristics of that entity type. Okay, so let us formalize things a little bit now. In the ER model or the entity relationship model, we have a standard notation of representing entity types and their attributes. As you can see in this slide here, entity types are represented by rectangles. Okay, so department is an entity, and attributes of the department like department name, department identifier, manager of the department and so on are represented in the form of ovals or something like balloons hanging over this entity types. Okay, so there are some definitions here. So if we review this, an entity represents an object of the real world that has an independent existence. Note the term independent existence. That is, you should be able to identify an entity independent of every other entity in the system. Okay, address is not an entity because address belongs to some entity called employee, okay, or department or whatever. Okay, however, the employee itself is an entity because it is an independent, independently occurring object in the UOD. Okay, and an entity has attributes which are properties that describe the characteristics of this entity. Okay, now what are the kinds of attributes or what are the different kinds of attributes that could exist? We saw name and age and date of birth and so on, but can we classify these attributes into different kinds of attributes, and can they tell us something about the characteristics of the entities? Okay, so there are several different classifications of attributes. We are going to look at a small number of such classifications. One of the first classifications of attributes is simple versus composite. Okay, so what is a simple attribute? A simple attribute is let us say something like age. Okay, you are 30 years old, 30, age equal to 30. Okay, so that's a simple attribute. There's just one value associated with an attribute. Okay, so when you say age, you get back one value called 30. On the other hand, suppose you say name. In some countries, okay, we just say name is name. You just talk about one name for an employee. But in several different places, we have when you talk about name, you have to specify a first name and middle name and last name and title and nicknames or whatever. So basically, a name is composed of several other attributes within it. So that is what is called as a composite attribute versus a simple attribute which has just one value. Okay, and there could be something like a single valued attribute or a multi-valued attribute. Okay, now what is a single valued attribute? Again, age is a single valued attribute. Okay, at any point in time, at least you have just one age, right? That is, at this point in time, let us say you are 30 years old or 35 years old or whatever. Okay, on the other hand, at any given point in time, an attribute may actually have multiple values. Okay, now take the color of a peacock, for example. Okay, no matter when you are going to measure this, no matter at what time you are going to take a snapshot of a peacock, you are always going to find many colors. Okay, so this is a multi-valued attribute. That is, the attribute itself is defined by multiple values. How is this different from a composite attribute? Let me pause here for a little while so that you can ask this question to yourself again. How is a multi-valued attribute different from a composite attribute? Now, composite attribute, if you notice closely, is made up of different sub-attributes. For example, name is made up of first name, middle name, last name, and so on. Okay, and initials, for example, or title, and so on. Okay, all of these need not be of the same type. I can say title can be either Mr., Dr., Mrs., whatever, and so on. Okay, only these three types. On the other hand, name could be anything, any string, and so on. Okay. On the other hand, when we look at multi-valued attributes, all the different values that it takes, color of a peacock, for example, it might have different attributes, many attributes, but all of them denote color. Okay, blue, green, red, white, whatever, all of them are color, all of them are the same types. Okay, so a multi-valued attribute are different values of the same attribute type, but a composite attribute is a collection of different smaller attributes in itself. Okay, and then there are what are called as stored attributes versus derived attributes. Okay, now stored attribute is something which you just store in the database, your date of birth, for example. Okay, so when you ask what is your date of birth, you just give some date and then store it in the database. Okay, however, suppose you were to ask what is the age of an employee. Okay, now suppose you know today's date and you know the date of birth of the employee, you can always derive the age of the employee, right? So age in a sense is a derived attribute. A good database design would put age as a derived attribute because a database hopefully is going to be used for a long time, right? It's not just today. Today an employee might be 30 years old, but 5 years later he still won't be 30 years old. He would be 35 years old, right? So it's always best to have age as a derived attribute, because you always know what is the current date, and you always know the stored attribute called the date of the birth. Okay. Similarly, there are what are called as null attributes, or null values for attributes. Sometimes an attribute may not have any associated value for a particular case. Okay. And let me give an example. Suppose a student can take at most 2 elective courses in a semester, okay, and at least 1 elective course and at most 2 elective courses. Okay. Now let us say there is a student who has taken just 1 elective course. Okay. Now because he can take at most 2 elective courses, there are 4 different there are 2 different slots, okay, elective 1 and elective 2. Okay. Now let us say after at the end of the course he is given a grade for each of the courses that he has taken up. Okay. Now he gets a grade for the first course, but he doesn't get a grade for the second course because he didn't take the second course at all. Elective 2 has no grade, but this grade is not we can't say that he has scored 0 in elective 2. Okay. So a null value is different from 0 or unknown or missing value. Okay. This is not a missing value, this is not a this is not 0, or this is not an unknown value, this is a null value. That means that it's something like when you say NA when you write in application forms, this is a null attribute. Okay. So let us come back to entities and define a few more terms here with respect to entity types. Okay. So we saw that an entity type, okay, I've been using the word entity type, but have never really formally defined this term, right? So an entity type is a definition or defines a collection of different entities of the same type. Okay. For example, in this slide we give this example of department. Okay. So a company could have different departments, but when we say an entity type department, it means that it represents all departments in the company. Okay. So it is a definition of a real world object type. Okay. So it's not this department or that department, it is just department, it is a type that the entity is going to be defined. Okay. Now any specific collection of entities of a particular type is what is called as an entity set. For example, if we take supplies departments plus accounting department. Okay. Now suppose we take both of them in some collection, we call this as an entity set. These are 2 different departments of the same entity type. Okay. So we also say that an entity type as opposed to an entity set. Okay. So an entity type is said to describe the schema or the intention of an entity set. What does that mean? It basically says that how should the structure of this entity or entities of this type look like. Okay. So suppose we say that department should contain a department ID, it should have an address, it should have a manager, it should have several other attributes. That means that no matter whether it is the supplies department or the accounting department or the systems programming department or whichever department it is, they should be defined by these attributes. That is, they should have a department identifier, they should have a clearly defined address, they should have one person designated as manager, and so on. Okay. So so an entity type describes what is called as an intention or the schema for an entity set. Okay. Or different entities of the same type. So here are again a review of the representations. Entity types are defined by boxes, and attributes are defined by ovals, and different kinds of attributes have different kinds of ovals. Maybe it's not completely visible here. The multi-valued attributes are defined by an oval having a double line. Okay. And similarly, derived attributes are those which can be derived from other attributes, are defined by a dotted line instead of a solid line. Okay. And we now come to another key issue when we are talking about entity types, and namely this is about key attributes. Okay. Now what is a key attribute? Now if you notice carefully, when we said that each department has to have a department identifier and a manager and a address and so on, okay. Now why do we need a department identifier for each department? This is to be able to identify each department uniquely, okay. Now if I say department number 10, it means just one department, no matter what its name is, okay. Department name could be ambiguous, it could mean supplies and accounts, and suppose we might have a department called administration, it might mean both supplies and accounts or whatever. So a name could be ambiguous, but when we say an ID or an identifier, it's something like what you have a pin code in postal addresses. It uniquely identifies each entity of this entity set, okay. So the department ID attribute is unique for each department that belonging to this entity set, okay. So such attributes which can uniquely identify entities are what are called as key attributes or keys, okay. So the key attribute, as you can see here, is specified by an underlined definition, okay. So the department ID is underlined here to denote that it is a key attribute. Now in some cases it need not always be just one attribute that's the key attribute, okay. There could be more than one attributes which are key attributes, in which case all attributes which form part of the key are all shown underlined, okay. Now what is meant by a key attribute? So an attribute or a set of attributes that uniquely identify entities in an entity set, so it's what is called as a key attribute. Now like I said, it need not be just one attribute that is a key attribute, there could be more than one attributes which is a key, okay. So in which case the key attribute is called a composite key, okay. So it's the key is made by combining two or more attributes together. Now a composite key should be minimal. What does it mean to say a composite key is minimal, okay. Let me first give you the definition of what is meant by minimal, and then we can see an example, okay. So no subset of a composite key should be a key itself, okay. For example, let me take the attributes department ID and department name. Is it a key attribute? Of course it's a key attribute, okay, because if I take department ID, department number 10 supplies, it uniquely identifies one particular department, okay. However, the second attribute here, the name called supplies, is redundant. We don't need to have this attribute here in order to uniquely identify a department. It's sufficient enough if we say department number 10, okay. So that's what is meant by a composite key, that is department ID and name is not a composite key because it is not minimal in nature. No subset of a key attribute should be a key attribute in itself, in which case this is not so, okay. So key attributes are shown underlined in the ER diagram. There are also certain other properties of keys which we are going to revisit again when we are going to look into the enhanced ER model, okay. What is called as the retention of key attributes in all extensions, okay. So let me not take this property right now, and we will come back to this again, that the key attribute should be retained for all extensions of a particular entity type, okay. Now it may so happen that a key attribute should uniquely identify an element, okay, but an element need not have just one key attribute. Of course I can have two keys to my house, right, key from the front door and the key from the back door, okay. Now it is fine, but the only thing is this key should open only my house door, not somebody else's house door, okay. So that's the idea, that is a key should uniquely identify a house, but a house could be identified by more than one keys. You could either enter through the front door or the back door, okay. Similarly I can have let us say on a computer network, you can uniquely identify a machine by its IP address or so to say Ethernet address on a LAN and so on, okay. But a machine could have more than one Ethernet cards, in which case both of them uniquely identify the machine, okay. So there is no restriction on how many keys that you are going to have, okay, but usually we are going to use one key, so what is called as the default key. Usually we are going to enter through the front door, okay, not always through the back door, right. So usually we are going to use just one key, but you may have more than one keys that define a particular entity type. And there could be some entity types which have no key attributes. Okay, we are going to take a look at one such example a little later on, and it may not be possible to define any kind of a key attribute for such entity types, and such entity types are called weak entity types, or entities of such types are called weak entities. Okay, so they have to what we call as totally participate in some relationship in order to define themselves. Okay. Now we come to the next definition of definition in the ER model, what is called as a domain. Okay, what is meant by a domain of attributes? Okay, now a domain, to put it in a very informal fashion, is going to show you the space in which an attribute is going to be defined. Okay, for example, if I say age of an employee, okay, and there are some set of rules that you cannot have employees lesser than 18 years and greater than 65 years. The domain is basically the a number between 18 and 65. Okay, obviously it can't be there are also some physical limitations in the sense that the domain of an age can never be negative. Okay, so that's a nature imposed restriction, but there could be other restrictions, and which basically defines the space within which any value of this attribute can reside. Okay, now if a composite attribute has different sub attributes, or like we saw, name has different sub attributes, first name, middle name, last name, and so on. Okay, so and each of them have their own domains, let us say D1, D2, and Dn. So so we see that the domain of the composite attribute is Cartesian product of the domains of individual attributes. So the first attribute can take a value between 18 and 65, and the second attribute can take a value between 0 and 10, and so on. Okay, so the domain of the entire attribute is just a Cartesian product of all of these domains. Okay, so let us briefly come back to this company example and see whatever we have seen until now. So we can think of different kinds of entity types like department, project, employee, and so on, and there are different kinds of attributes for each of these entity types, and there are certain key attributes here which are underlined, and then there are certain composite attributes which are shown like this, that is, name is composed of first name, middle name, last name, and so on, and like that. So and several other entity types that we can identify during our analysis. Okay, the next concept, that important concept that we are going to be looking at in ER modeling is the notion of relationships. Like the modeling itself says, it's about entities and relationships. Okay, so we just until now we looked into what are called as entity types. Okay, so we defined an entity type, an entity set, attributes, different kinds of attributes, and keys, and domains, and so on. Okay, now let us see how can we relate entities of different types. Okay, so a relationship, or to be precise, relationship type defines a relationship between two or more entity types. Okay, so the slide here shows a relationship type, okay, between an entity type department and an entity type employee. Okay, and it says managed by. Okay, so it basically says a relationship type specifies that any department or any entity of type department should be managed by some employee or some entity of type employee. Okay, so let us go further and make some definitions. Okay, first of all, let us first define what is meant by relationship type. Okay, so relationship type R is an association. Okay, is an association among different entity types. It need not be just two entities, it can be any number of entities. Okay, so so there could be n number of entities, and defines it basically defines a set of associations. Okay, what is called as a relationship type. Okay, so if you look at it a little bit carefully, a relationship type is just a subset of the Cartesian product of all of the entity types. Okay, so that means an entity instance or an entity of this type could be related to some entity of this type, and some other entity of the next type, and some other entity of the next type, and so on, and all of this define one instance of this relationship. Okay, So let us delve deeper into what are meant by relationships and what are some of the characteristics that define relationships. Okay, firstly, the notion of the degree of a relationship type. Okay, so what is the degree of a relationship type? It's simply the number of entities that are involved in this relation. It is between how many relations is this relationship going to establish an association. We saw earlier a relationship type of degree 2, that is a department is managed by an employee. Okay, so there are two entities that participate in this managed by relationship. Okay, such kinds of relationships are called binary relationship. Binary basically because there are two entity types involved. Okay, similarly there could be unary relationships, there could be ternary relationships, and so on, and there could be n-ary relationships, n different types of relationships. Okay. Now next we come to a kind of a tricky problem here. Now have a look at this slide carefully. The first picture above shows the relationship type. Okay, it shows employee works for department, and the second relationship and the second picture below shows employee as an entity and department in which the employee works in as an attribute of employee. Okay, so which is correct? Is department an attribute of employee? That is, does the department in which an employee works in describe the characteristics of an employee, or is it that departments and employees have separate existences or separate entities, and there is a relationship type between them? Okay, so let me confuse this problem even further. Take a look at this slide here. Okay, so in the earlier slide you could have probably said that no, department cannot be an attribute because department has an independent existence. We already saw that each entity type should have an independent existence, right? So because departments have an independent existence, they can't be an attribute. Okay, but have a look at this slide here. Okay, the first picture shows employee works for department as a relation, and then department has a department ID as one of its attributes. Okay, now I am going to take this department ID attribute and put it into employee and says employee works in this department. Okay, so this employee is associated with this department ID. So now which is correct or which is wrong? Okay, so is the first one correct or the second one correct? Well, the answer to this obviously is it depends. Okay, it depends on the particular situation in which you're looking into. Okay, now the first one where we show that employee works for department as a separate relation depicts the relationship between employee and department. Okay, and the second one just depicts what are all the different characteristics that describe or what are the different attributes that describe the characteristics of employee. Okay, that means if I am talking about an employee entity, okay, and if I say that an employee is or in some sense an employee is very closely tied to his department. Okay, so he has no identity without his department ID, in which case you have to say department ID is a part of the attribute or is one of the attributes of the employee entity type. Okay, so relationships versus attributes, it's a slightly a tricky problem always in order to determine whether a particular thing is actually a relationship or is it an attribute. Okay, and in some kinds of data models like what are called as functional data models or in object databases, relationships are almost always referred to as in the form of attributes. Okay, for example, in object databases you talk about relationships by storing an object reference. Let us say you have a relationship between employee and department, so there is a reference to a department object within the entity object and vice versa, and a reference to an employee object in the department object and so on. Okay, similarly in relational databases, which we are going to study much deeper, we see that relationships are established by what are called as foreign keys. Okay, that is there is one table that describes one kind of an entity and a relationship between this table and the other table is described by a foreign key attribute which says that this entity of this type is related to some other entity of the other type. Okay. Now we come to another important issue when we are talking about relationship. This is the notion of constraints. Okay. So what is when we talk about relationships, almost always relationships are defined by certain kinds of constraints. Take the example of employee managing a department. Okay. One of the most simplest constraints that we can think of is a department should be managed by at most just one employee. Okay. We can't have two managers or two heads of a department. We should have just one head of a department. Okay. And we might also establish a constraint that one person can manage at most one department at a time. In some cases, there could be allowed to manage more than one department at the same time. Okay, so that means in that case there is no constraint from employee to department, but there is a constraint from department to employee. Okay, so when you are talking about constraints in relationship types, we are mainly concerned with two kinds of constraints, what we call as cardinality ratios and participation constraints. Okay, so what are these cardinality ratios and participation constraints? Let's have a look at them. Okay, so take a look at this relationship again here. Now I've replaced this managed by with another relationship called works for. Okay, now works for is slightly more general than managed by. Okay, in which way is it more general than managed by? A department can have many employees working for it. Okay, however, we might have to sometimes we might have to mandate a requirement that an employees can work for only one department, not for multiple departments. Okay, so so this is shown by these shown in one of two different ways, either like this, that is n:1, which says that n employees to one department, or something like this. Okay, so it says it could be n employees working in one department and so on. Okay, so so on the other hand, what happens if this were to be m:n? Okay, something like 4:3 or 2:1 or 2:5 or something like that. Okay, so that means that let us say 4:3. Okay, so that means that a department can have at most 4 employees, and an employee can work in at most 3 departments and so on. Okay, so so basically you can represent a cardinality constraint or a cardinality ratio in this case that says participation in this constraint is defined or constrained in this by these cardinalities or number of entity types. Okay, the second kind of constraint that that's important is what are called as participation constraints. What is a participation constraint? Take a look at this slide here. Now this slide shows another relationship type which says department and handles project. Okay, now a department may handle several different projects. Suppose there is a restriction that a project has no existence unless it is associated with a department. Okay, now suppose I have a project for developing some kind of software. Now this project does not exist if it is not associated with some department, if there is no department which is in charge of this project. Okay, basically what this says is that if every project has to be associated with a department, then the very existence of project depends on this relationship. So only if an instance of this relationship exists, only then can a project entity type exist. Okay, or such kinds of constraints are what are called as participation constraints. Okay, they are defined by a double line here. Maybe it's not fully visible, but it is a double line here. Okay, so that means that the very existence of project is dependent upon the existence of a relationship of this kind. Okay, going on further into participation constraints, we say that the entity type, in this case project, is said to totally participate in this relationship, because if it doesn't participate, it doesn't exist anymore. Okay, so a participation constraint in which an entity type's existence is dependent upon the existence of this entity type of this relationship type is called as total participation. That is, the entity type participates completely or totally in this relationship. Okay. We can also think about attributes for relationships and not for entities themselves. Okay, just like we saw attributes could be associated with entities, we could also allocate attributes for relationships. Okay, now have a look at this figure here. It shows department as an entity type and says that department handles certain projects. Okay, so and project totally participates in this relationship, and then an attribute called budget is placed for this relationship. Okay, so what does this mean? It basically means that this budget or the budget that is specified here is allocated for this project associated with this department, or is specifically allocated for this relationship type. Okay, so in cases where, let us say, the project is handled by more than one department, okay, that means that this budget is not allocated to the project. Okay, this is allocated only for this project for working on this department and so on. Okay, it is not allocated to the department as well. That means the department cannot use this budget for anything else. It has to use it for this project only. Okay, so so this budget actually is a constraint on the relationship type. Okay, so it belongs neither to the department nor to the project in its entirety. However, there are certain kinds of relationships where we can actually move the attributes from the relationship type to one of the entities. Okay, what are those kinds of relationships? Take a look at this slide here. The first figure shows a 1:n relationship. That is, a project can be associated with at most one department. Okay, and there is there is an attribute called budget that is allocated to this relationship. Now, if you see carefully, we do not lose correctness if we move this budget attribute from the relationship to the project side. Okay, so if I say that this budget is allocated to this project, it does not lose any semantics, because a project can be associated with just one department. In the previous slide, a project could be associated with m different departments. That is, it could be associated with many departments. Okay, so here, since a project can be associated with only one department, it does not lose semantics if the budget is allocated to the project itself. Okay, so one of the last things that definitions that we will be looking at today is what is called as an identifying relationship. Okay, have a look at this slide here. The slide here shows a figure where an employee is identified by his PAN number. Okay, so assuming that every employee is a taxpayer and has received a PAN number from the government, an employee is uniquely identified by his PAN number. Okay, now let us say we prepare the company prepares some kind of an insurance record for each employee. Okay, now let us say this entity called insurance record, which contains certain parameters or whatever, okay, is an entity by itself, right, because it has an independent existence. Okay, you can see an insurance record and note that it's an entity by itself. However, you see that an insurance record has no existence, has no meaning unless it is associated with somebody, unless it is associated with some employee, some department even, or whatever. Okay, so this is an example of an entity type which is a weak entity type. That means it has no keys. Okay, the key for the insurance record is of course the PAN number itself, or PAN number of the employee. Okay, so the key of the employee which defines an insurance record is forms the key for the insurance record as well. Okay, and the relationship that defines this such a kind of association is what is called as an identifying relationship. Okay, so this relationship here in this slide, which is called as insurance details, identifies insurance record with an employee. It basically ties in insurance records with employees, so that an insurance record also gets independent existence by themselves. Okay, so as you can see, insurance record totally participates in this relationship. Obviously, it has to totally participate in this relationship, but on the other hand, not every total participation may mean an identifying relationship. We actually saw an example earlier where we saw two different entity types, department and project, in participation, but which is not a weak entity type. Okay, so identifying relationships are again defined by double lines on the relationship types itself. Okay, so so let us briefly pursue a summary of the different notations we saw. The first thing that we saw was an entity type and defined by a box, and a weak entity type which is defined by dotted line, which is not clearly visible here. Okay, then relationship types are defined by a rhombus, and the identifying relationship types are defined by double lines. Okay, similarly, attributes are defined in different ways. That is, a normal attribute is an oval, a key attribute has an underline there, and a multi-valued attribute has a double line, and a derived attribute has a dotted line. Okay, so so with this we come to the end of this session, where we had a brief look at what is meant by conceptual design of a database. Okay, so to briefly summarize that, a conceptual design of a database is meant for non-technical users. It's a high-level design, and mainly composed of diagrammatic notations like entities and attributes and so on. And within this diagrammatic notations, we saw that there are several different characteristics. There could be entities, entity types, entity sets, attributes, multi-valued attributes, and key attributes, and relationships, and identifying relationships, and weak entity types, and so on. Okay. So one of the first steps that we do in database design is to be able to identify these entity types and relationships, and to be able to build this ER schema. Okay, so that brings to the end of this first session on conceptual modeling of database systems. Thank you.